Hey, in this video here, I'm going to try to teach you how to find the rotational inertia of something by actually doing the integral calculus. We know a bunch of rotational inertias. You know that a disk is 1/2 mr squared and so on and so on. But what if you have something and you either need to find its rotational inertia because you don't know it, or because somebody tells you to do it that way. Here's the key. Once you know this, there's one other thing that you need to know. You need to know what the linear mass density, which is this function. Oop, I need to do that. The linear mass density, let me just explain what that is, as a function of r, tells you how much mass you have at some distance r or x or whatever you're calling that distance away from the axis. That's what this function is. So you need to know that, because if you do know that, so this is like how much mass at distance r from axis. If you know that linear mass density function, then the mass of the whole thing is equal to the integral of that from 0 to r. And if you replace that big M and the big R with variable, like, well, I don't know if I wanted to go all the way to the edge, so what if I just go, for example, to some distance r, and then it would give me this variable m. And then if you take the derivative of that, what you're going to find by the fundamental theorem of calculus is that the linear mass density dr is equal to dm. So the important thing here, I would like you to write this down on your formula sheet right here next to this, just in case you need that. So this is always going to be true. And the situations that you are going to run into where you might possibly be asked to do this will fall into one of two categories. It will either be a uniform thin rod, like the first two examples that I'm going to do here, or it will be another situation where they just give you this linear mass density. For a thin rod, the linear mass density is just a constant m over L. Where this is the distance from the axis. It's that constant because you don't get any more or less mass as you move out, because it's just a thin rod. So this is the simplest situation. This is the only situation where they're not going to give you that linear mass density. So I don't know, maybe that's another thing you want to just have in your notes at the ready for thin rod. For thin rod, the linear mass density is this. Okay, so let's try that and see how this works. So we know that the integral from 0 to L, that's the full length of the rod, is, if we want to find the rotational inertia, that's going to be this integral of r squared dm. Now, what's what here? The problem with this integral, with doing these, the reason we have to do all this stuff is because dm is not the same as this variable r, right? So we need to make them the same. So I know that dm is equal to the linear mass density dr. So that's what we need to do, just make that substitution. So I need to do integral from 0 to L of this. What's the linear mass density of a rod? It's just m over L. times r squared. And now I've changed it to a dr. So that's the trick here. So what happened? I just made this substitution. It's very U substitution-ish what we're doing here. So here, that dm turned into this, and that's going to be the trick every time. So there's the m over L part, and there's the dr part, right, using this. Okay, so pause that for a second and just kind of hang out with that, with those expressions. Once we have that, then the calculus part's quite easy. And I think this part, it's pretty easy to do this once you get the hang of it. And we'll do a couple examples here. So, okay, so let's see. This m over L, those are constants. That's just the whole mass and the whole length of the rod. And so I need, what's the antiderivative of r squared dr? That's r cubed over 3, and I'm going from 0 to L. All right, so what do we have here? I need to plug in the L, so I have m over L times L cubed over 3 minus what I get when I plug in 0, which is just 0, and one of the L's cancels out, and I get m L squared, squared over 3, which was the goal. All right, so that's how that works. Here is another example, also with a thin rod. So that means these are the things that I'm going to be thinking about if I'm asked to do this. I'm thinking about that the rotational inertia is the integral r squared dm, and I'm thinking about that dm is equal to the linear mass density times dr. And since this is a thin rod, I know that the linear mass density is just m over L. Okay, so I'm just going to give you one other tip here, and then I'd like you to pause this and just try to do this problem real quick. The trick with this one is this is where the axis is. So I have from here to here, I need to integrate from here to here, and then I also need to integrate from here to here. There's like two different pieces of this. So what I'm going to do, I'm going to think about setting up that integral from 0, that's where the axis is, you have to start at 0, to the edge, and if that's L over 3, then that would be like to 2L over 3, right? That's 2/3 of it, of r squared dm, plus, then I've got another piece sticking off the other end, which is the other third of it. So I have to do those two things. That's one way of doing this. You can, in the scoring guide, which you can look at, this is from, I don't actually remember which year this is from, but they were fine with you finding it from the middle and then doing the parallel axis theorem to it. You could do that. I'm going to do it this way, and I'm going to advocate for you doing it this way because we just learned how to do this. So go ahead and pause the video and try that and see if you can get that to work. Okay, so let's see how we do this. I need to do the integral from 2L over 3, 0, r squared dm. And the disagreement of the r squared and the dm, that's the problem. But I know that this is true. I can make that substitution. So this integral turns into 0, 2L over 3 times m over L times r squared dr. Right? So the dm turned into those things. Why? Because the dm always turns into the linear mass density dr. That's the trick. Okay, so let's see what this turns into. So I have m over L on the outside, and then on the inside I have r cubed over 3, So I'm going from 0 to 2L over 3. And then I'm going to have to do the same thing here and add these together, right? This is for the other piece. This is the 2/3, 0 to 2/3, and this is the 0 to 1/3 L. All right, and I'm going to add them up. 0 to L over 3. Okay, so let's see what we get for this one. I've got M over L times this cubed. So 2L over 3 cubed is, let's see, 8L cubed over 27. And then over this 3, I'm just going to move that to the outside and put it here. This is messy enough. And when I plug in 0, of course, I get 0. And then for the other piece, I'm going to move that 3 to the outside also. So M over 3L. And I get L, let's see, so that's L cubed over 27. Okay, so, well, I've got like fractions here. I've got 8 27ths and 1 27th of these. So when I add those together, I get, let's see, 8 plus 1 is 9. 9 27ths is 1/3. So I get M over 3L times L cubed over 3, right? Because I had 9 27ths of that. And that is, one of the L's cancels out, so I get ML squared over 9. And that was the target right there. All right, so not too bad. There's some fractions there, but getting that set up, knowing how to get that set up is important. Okay, so let's see what one looks like where, looks like somebody already wrote on this, where it's not a thin rod. So it's still true that dm is equal to the linear mass density times dr. Just notice here that the linear mass density has an r in it because it's variable now. It's not just the constant like the thin rod. And does that make it harder? Not really, because they're telling us what that linear mass density is. So I think we should be good. Okay, so how do we do this? I know that the integral, let's see, where do we need to go? What are my limits of integration? I start at the center and I go to the edge of the object, and that's this r. So 0 to r, and r squared dm. And I know that probably you want to write this down. Actually, not probably. Definitely you want to write this down here so that College Board knows that you know what you're doing. So that's always true. I think that it's probably fine to just drop this on them, which is all the more reason to have it on your formula sheet there. Okay, so making our substitutions, I have r squared, the dm is going to turn into, let me write down this first, it's going to turn into this, so that's m r over 25 big R squared, that's this, times r squared dr, right? So this and this, that's what's replacing the dm, okay? And I'm going from 0 to r. Now, what's a constant and what's not a constant? That will make it a little easier to do this. The m and the 25r squared, those are constants. And then this r and these. So now I have 0 to r cubed dr. When I find the antiderivative of that, that is equal to r to the 4th over 4 from 0 to r. And plugging in the r, I get big R to the 4th over here, 4 times 25 is 100, r squared, and some r's cancel out. So it looks like I have m r squared over 100. A couple of comments about that. You should get some constant times an mr squared. You have to get something that is dimensionally correct for being a rotational inertia. So some kind of ml squared or mr squared with some constant. And in retrospect, if this is some kind of disk here with a disk of mass m and radius r, if it was a uniform disk, then the total of the whole thing would be 1/2 mr squared. So this is like 1/50th of that. So that's suggesting to us here, well, maybe this is like, if you imagine it was a pizza cut up into 50 slices, we're talking about one of those little slices here. So that kind of makes sense. It's a little wedge of that. And then here, derive an expression for the rotational inertia of the modified disk, the disk after the narrow wedge is cut out. Well, if it is a uniform disk, so that means we have I disk, if we're removing a wedge, these are just like masses. This is like cutting off a little piece of mass. We just have to subtract that out. So I have mr squared over 2 minus mr squared over 100. Like with calculus, there's no need for you to simplify this, but if you wanted to, their common denominator would be 100, so multiplying by 50. So simplified, it'd be 49 mr squared over 100 after we remove that little wedge. That's a 4 there. All right. One more. So after having done that one, where is the other one? Is this the... My document seems to be kind of messed up here. All right, well, let me show you what the other one was. To move over to my computer, and I'll show you. It's from 2000 and let's see, 2018. Number 3. This is not from any secret test. These are just the 2018 ones that you can find on the College Board site. And they're giving us an object that's made out of a hoop and then 3 little wedgy kind of spokes that look like this. You can look up their picture if you want. And they're telling us that one of the spokes, which they call a triangular rod, has mass L, and length L, mass M, and it's got the mass density function of, sorry, that's a little too messy. It's got mass density function 2m over L squared times x, where x is the distance from here. Okay, so they want us to, using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2. Okay, so we just need to do exactly the same thing we did in the last problem. If you so choose, and you should, go ahead and pause the video and see if you can do that right now. So your target here is to get ml squared over 2, just like the last problem. All right, so here we go. So the rotational inertia of this thing is going to be integral r squared dm. We're going to go from 0 to the length of the rod. And here, it doesn't really matter at this stage, but really, we're not dealing with r's here. They're calling it x instead. So I could put an x there instead of an r. I don't think that would be a big problem if you put an r, so long as you make the substitution out here. Okay, so I also know that dm is equal to the linear mass density times dr. That is the key. I'm going to write that down there so the world knows that I know. And let's substitute out and see what it looks like now. So 0 to L, I've got my dm is going to be the linear mass density function, which is 2m over L squared x, right there, because they gave it to me. And then times the x squared, that's always going to be there, or an r squared. And then here, since it's in terms of x, that's going to be now dx. So we now have an integral that we can do. Let's see, what's constant and what's not? The 2m over L squared, that's all constant. And then integral from 0 to L, x cubed dx. So 2m over L squared, it's x to the 4th over 4 from 0 to L. Now that's 2m times L to the 4th over 4L squared. And sure enough, that gets me my ml squared over 2. Check. So the other part of this that I was going to show you is they wanted you to find, and this was their part A, and their part B, they wanted the rotational inertia of the whole thing. And part of what they want to assess here is if you understand that rotational inertias add up just like masses do. So this thing is made out of a hoop, like a rim, like a bicycle wheel, and these 3 spokes. So I just have to add up those things. I have the hoop plus 3, what do they call this, triangular rod? I'm just going to call it a spoke. All right, so, and they told us that the rotational inertia of the hoop is ml squared. You know that, and you're going to have that in your notes in front of you somewhere, but in this problem, they actually just told us. And then 3 of the spokes. So I got 1 plus another 1.5, I got 5 halves of an ml squared. That's the total. All right, so I would have some information, I think the key things to have in your notes next to this is to have a little star or whatever that tells you that dm is equal to linear mass density times dr. And this is either given or it's just m over L for a rod. All right, there you go, new stuff.